Picture a missile flying 4 meters above the ocean surface. Not 400, not 40. 4 meters, lower than the bridge railing on a fishing boat, low enough that spray from wave crests blurs its radar return into background clutter. It's doing roughly Mach 0.9. Its navigation system cross-checks inertial guidance against a terrain-following radar altimeter, sampling the wave surface 60 times per second, making micro-corrections to hold that 4-meter profile with mechanical precision. One target, the hull of an Arleigh Burke-class destroyer somewhere ahead. Here's the question that should bother you. The US Navy fields one of the most capable air defense systems ever put to sea. An Arleigh Burke carries the Aegis combat system, linked to the SP-1 radar, capable of tracking hundreds of objects simultaneously. It carries the SM-6 interceptor, a missile with a range measured in hundreds of kilometers, a price tag of roughly $4 million per round, and the ability to engage targets beyond the visual horizon. By any reasonable measure, the SM-6 is the more capable weapon. So why, when that sea-skimmer closest to the last few miles, does the job fall to a missile whose design lineage traces back to the 1970s? A round that costs a fraction of the price and fits inside a launcher originally designed. D for something else entirely? That's the paradox at the center of this breakdown. And the answer is not what most people assume. Start with the weapon trying to defeat the ship. Sea-skimmers, anti-ship cruise missiles that fly at extremely low altitude to evade radar, aren't new. The concept appeared in serious form in the 1970s, matured through the 1980s, and by the Falklands War of 1982 had already demonstrated what it could do when the Exocet hit HMS Sheffield. What has changed in the decades since isn't the basic aerodynamic idea. It's the variety, the speed, the terminal guidance sophistication, and above all, the sheer number of these weapons now available to potential adversaries. In the Western Pacific, the category of concern has expanded well beyond the Soviet-era designs that originally shaped NATO countermeasures. Chinese naval planners have developed a family of anti-ship weapons ranging from subsonic cruise missiles to faster, sea-skimming variants designed to operate in salvos, multiple rounds arriving from different bearings within a compressed time window. The logic isn't new either. Overwhelm the defender's engagement capacity by forcing simultaneous intercept solutions on multiple axes. The arithmetic of magazine depth and engagement timelines becomes the central problem. The Arleigh Burke-class destroyer entered service with USS Arleigh Burke herself in 1991. By 2026, the class numbers over 70 hulls in various configurations, making it by a wide margin the most numerous large surface combatant in the US Navy. Each ship carries the Mach 41 vertical launch system as its primary weapon magazine, a modular, below-deck launcher of cells arranged in strike-length and tactical-length configurations. On a standard Flight Thigh A Arleigh Burke, the total cell count runs to 96. Each of those 96 cells can hold one SM-6, or one SM-2 standard missile, or one Tomahawk cruise missile. Or, and this is the critical variable, a canister containing 4 RIM 162 evolved Sea Sparrow missiles packed in what the Navy calls a quad pack. 4 weapons where one would otherwise sit. That density difference is not a footnote, it is load-bearing. The SM-6 is a remarkable weapon. Its formal designation is RIM 174 Standard Missile 6, and it entered fleet service in 2013 after development through the early 2000s. It's built around the airframe of the earlier SM-2, but uses an active radar seeker derived from the AIM-120 AMRAAM air-to-air missile, meaning it can guide itself to a target without the launching ship's radar holding continuous illumination. A significant tactical advantage at long range. Its maximum engagement range against air-breathing targets is well over 200 kilometers in the right conditions, and its engagement envelope extends to the upper atmosphere for certain ballistic missile threats. Price per round is estimated at approximately $4 million. The RIM 162 ESSM, Evolved Sea Sparrow missile, occupies a different conceptual space entirely. Its roots are in the basic point defense missile system developed in the 1960s, refined through the RIM-7 Sea Sparrow programs of the 1970s and 1980s, and evolved into the current RIM 162 Block I and Block II variants now in service. The ESSM Block II adds an active radar seeker similar to the SM-6's, an important upgrade over earlier semi-active guidance. Its engagement range is roughly 50 kilometers against aerial threats, compared to the SM-6's hundreds. Cost per round is estimated in the range of several $100,000, substantially less than the SM-6, though not trivially cheap. On paper, this looks like a clean hierarchy. SM-6 is the long-range layer. ESSM is the short-range backup, everything arranged in tiers from far to close. The problem is that reality doesn't arrange itself in tiers. Reality arranges itself around physics. Here's the detail that stuck with me when working through the engagement geometry: the radio horizon. Every surface radar has a detection horizon determined by the curvature of the Earth. The SP-1 radar on an Arleigh Burke is an extraordinary sensor. It can track a basketball-sized object at altitude, and it connects to a fire control network spanning an entire carrier strike group. But it cannot see through the planet. A target flying at 4 meters above the sea surface, approaching from 30 kilometers away, is hidden below the radar horizon for almost the entire duration of its flight. The numbers are stark. Against a target flying at high altitude, an Arleigh Burke's radar might detect it at 300 kilometers or more, plenty of time for multiple SM-6 engagements at long range. Against a sea-skimmer flying at 5 meters altitude, the same radar might not achieve a confirmed track until the target is inside 25 kilometers. In some conditions, first detection happens at 15 kilometers or less. At Mach 0.9, roughly 300 meters per second, a target at 20 kilometers has 66 seconds of flight time remaining before it reaches the ship. At 15 kilometers, that falls below 50 seconds. 50 seconds from first detection to impact. That is the entire engagement window for the close-in defense. Now run the SM-6 through that timeline and see what breaks. The SM-6 is optimized for long-range engagements. Its flight time out to ranges of 100 kilometers and beyond is measured in minutes, not seconds. It's built to fly far, climb, maneuver, and use its active seeker to hunt a target across a large volume of airspace. At close range, inside 20 kilometers, the SM-6 faces a series of problems that have nothing to do with its quality as a weapon and everything to do with the physics of the engagement geometry. At close range, the target is arriving fast and low. The intercept geometry is compressed. The launch to intercept timeline is extremely short. The SM-6 needs time to motor away from the ship, transition to its cruise phase, and then execute a terminal intercept. And at ranges inside 15 kilometers, that sequence becomes geometrically awkward. The missile was not designed for the compressed angles and minimum time intercepts of a close-in engagement. This is not a defect. It's a design choice. You don't engineer a long-range interceptor around the last 5 seconds of a Sea-Skimmer's terminal run. What you do instead is keep a different weapon for that job. The ESSM is purpose-built for exactly this geometry. It's agile, with high maneuverability at short range. It accelerates hard off the rail and reaches intercept velocity within seconds of launch, giving it the energy budget needed for the angular rates of a close-in intercept. It can be launched rapidly in succession. And in quad-pack configuration, 4 of them occupy the space a single SM-6 would require. Most people assume the most expensive weapon is always the right answer. What the evidence tells us instead, the right weapon is the one whose engagement envelope matches the physics of the threat. Against a sea-skimmer inside 20 kilometers with 50 seconds to impact, ESSM is not the cheap consolation prize, it's the correct tool. Put yourself in the position of the ship's combat systems officer for a moment. The SP-1 radar has just acquired a fast, low target at 18 kilometers. Contact classification takes 3 to 4 seconds as the Aegis system correlates the return against its threat library and confirms this isn't a surface wave artifact or a spurious track. You have, generously, 45 seconds before that object reaches the hull. You can fire a single SM-6, optimized for a completely different engagement geometry, or you can fire 2 ESSM rounds in rapid succession from a quad pack, each with a seeker designed for close-in intercepts, with enough rounds remaining to address a second incoming target in the same salvo. Which option actually addresses the threat? The answer the Navy arrived at, after considerable analysis, is that the ESSM quad pack fills a role that no amount of additional SM-6 inventory can replicate. Here is where the magazine math becomes the strategic variable. An Arleigh Burke with 96 MiG-41 cells has a finite magazine. In a real-world mix, some cells carry Tomahawks for land attack, some carry SM-2 for area air defense in mid-tier engagements, some carry SM-6 for long-range and ballistic missile defense, and some carry ESSM quad packs. The exact mix is classified, but the trade-off is real and documented in public budget and procurement discussions. Every cell allocated to SM-6 is one cell that cannot hold 4 ESSM rounds. The arithmetic is direct. If a ship allocates 20 cells to SM-6, that's 20 long-range interceptors. If those same 20 cells held ESSM quad packs instead, the ship would carry 80 close-in interceptors. Against a salvo threat, 5 or 6 sea-skimmers arriving simultaneously from multiple bearings, each inside 20 kilometers. A ship with 20 SM-6 rounds and a shallow ESSM inventory faces a dangerous arithmetic problem. A ship with a deeper ESSM load can allocate 2 rounds per incoming target across a wider salvo without exhausting its close-in magazine. The strategic implication runs further than a single ship. In a carrier strike group engagement in the Western Pacific, the Arleigh Burke destroyers and Ticonderoga-class cruisers form the inner defensive screen. If adversary planners are designing salvo attacks to saturate that screen, the volume of close-in intercept capability becomes the constraint on how large a salvo can be defeated. And volume in the MiG-41 system is a function of exactly this quad-pack density calculation. Going through procurement records and congressional budget justification documents, one figure kept coming back. The ratio of ESSM rounds on contract to SM6 rounds on contract in recent fiscal years reflects the Navy's own judgment about where the consumption risk is highest. The close-in layer is the one being filled deepest. The cost asymmetry between the two systems is worth examining on its own terms, because it connects directly to a larger strategic dynamic in the Western Pacific. The SM6 at roughly $4 million per round represents a significant investment per intercept. The ESSM Block 2 at several $100,000 per round is expensive by civilian standards, but represents a meaningful cost advantage at scale, approximately a 10-to-1 ratio per round when the estimates are compared directly. What makes this matter strategically is the Adversary's production math. Chinese defense industrial planners have invested heavily in anti-ship cruise missile production capacity. The DF-21D and DF-26 anti-ship ballistic missiles occupy the long-range layer of their A2/AD, anti-access, area denial, architecture. But in the sub-horizon, close-in threat category, subsonic and supersonic anti-ship cruise missiles represent a volume threat that could, in a sustained engagement, drain a surface group's magazine faster than it can be replenished at sea. That production asymmetry is worth sitting with. A single anti-ship cruise missile in the relevant Chinese inventory costs a fraction of an SM6 round. An adversary capable of fielding salvos of 40 or 50 missiles per strike package. And open-source assessments of Chinese naval air arm capacity suggest numbers in that range are plausible for a major engagement. Is not facing a symmetric cost exchange with a US surface group that must spend $4 million per SM6 intercept. The math of sustained attrition favours the offence when the offence is cheaper and the defence has a fixed magazine. Here's the take that will generate some pushback. The Navy's current magazine depth, even with quad-pack ESSM, is inadequate for a sustained high-intensity engagement against a peer adversary operating at scale in the Western Pacific. The Mach-41 system is an exceptional launcher, and the Arleigh Burke is an exceptional platform. But a destroyer that expends its ESSM inventory in a multi-wave engagement and then has no close-in intercept capacity is a platform that the next wave defeats with subsonic rounds that a phalanx CIWS must handle alone. Phalanx is a last-ditch system, not a primary defense layer. The math of magazine depth versus adversary salvo capacity is the real constraint that procurement planners are working against, and no amount of individual missile excellence changes the arithmetic of finite cells. What strikes me about where this program sits in 2026 is how clearly it illustrates a tension running through the entire surface warfare modernization debate. The requirement to hold range, to engage threats before they become close-in problems, conflicts directly with the requirement to hold volume in the magazine for the cases where range doesn't solve the problem. The SM6 is the right answer for the threat that appears at 200 kilometers. The ESSM is the right answer for the threat that appears at 15 kilometers with 40 seconds remaining. The problem is that a real adversary, designing their attack geometry deliberately, will attempt to present both problems simultaneously, forcing the ship to have already made its magazine allocation decision before the engagement begins. That allocation decision is irreversible at sea. You cannot reload an Arleigh Burke underway in a combat scenario at anything like the rate needed to sustain a multi-wave engagement. The nearest naval replenishment options may be days away. The cells you filled before departing port are the cells you have for the duration. This is the obstacle every surface warfare planner faces and has no elegant solution to. The Mach-41 cell count is fixed at 96. The threat taxonomy keeps expanding. The mixed decision. More SM6 for long reach, or more ESSM quad packs for close-in volume? Is a zero-sum trade inside that fixed number? Here's the part that doesn't sit right, even now. The Navy has known since at least the 2010s that magazine depth against salvo threats was the binding constraint in the Western Pacific scenario, and the Mach-41 cell count on an Arleigh Burke has not changed. The Flight 3 destroyers entering service now add the AN/SP6 radar, a significant capability improvement for detection and tracking, but they don't add cells. The radar gets better at seeing the problem earlier. The magazine does not get deeper to address it. The layered defense architecture that ESSM fits into has one more dimension worth examining: the role division between the outer, middle, and inner layers, and how ESSM sits at the intersection of the middle and inner zones. A carrier strike group in the Western Pacific deploys its defensive architecture in concentric rings. The outermost layer, area air defense at ranges exceeding 100 kilometers, belongs to SM6 and to the E-2D Advanced Hawkeye Airborne Early Warning Aircraft, which extend the radar horizon by being airborne and can cue intercepts before the ship's own SPWE radar has line of sight to the threat. The E-2D flies at altitude, meaning its radar has a vastly extended horizon compared to any surface ship. It can detect a sea-skimmer at ranges the ship cannot achieve and pass that targeting data down to the Aegis fire control network before the SPY-1 or SPY-6 has acquired the contact independently. In this layer, the SM6's range and active guidance are the decisive advantages. The middle layer, inside 100 kilometers but outside the radio horizon problem, is where SM2 and SM6 both operate, with the Aegis system coordinating engagement sequencing across multiple ships. This is where coordination between destroyers and cruisers multiplies the effective intercept capacity, because multiple ships can engage the same threat stream from different angles. The inner layer, inside the radio horizon for Sea-Skimmers, roughly 25 kilometers and closing, is where ESSM takes over. And inside 5 kilometers, where even ESSM may have insufficient time, the Phalanx CIWS and the RIM 116 rolling airframe missile, RAM, form the terminal layer. Each layer exists because the one outside won't achieve 100% intercept rates. The assumption embedded in layered defense is that leakers will exist. The question is whether enough layers remain functional to address the leakers before they reach the hull. The percentage of intercepts that the close-in layer is expected to handle in a realistic salvo scenario, accounting for leakers from the outer and middle layers, is not publicly stated in precise terms. But the procurement volumes tell the story. ESSM buy rates have consistently outpaced SM6 buy rates in recent fiscal years on a per-round basis, reflecting the Navy's assessment that the close-in magazine is the one most at risk of running dry. Think about what that procurement signal actually means in practice. Naval procurement cycles are long. The rounds being ordered today fill magazines that will be carried into engagements 5 and 10 years from now. When program managers consistently prioritize ESSM volume over SM6 volume in their annual budget requests, they're encoding a judgment about which layer faces the greatest depletion risk in a realistic fight. That judgment has been consistent enough, across enough budget cycles, that it is not a planning artifact. It reflects a structural assessment of the threat. What do you think? If the radio horizon gives you 45 seconds and a finite magazine, is the Navy better served by filling more cells with quad-pack ESSM to maximize close-in volume, or holding more cells for SM6 to push the engagement as far out as possible before the geometry compresses? Comment your reasoning. The real answer is not as clean as either option suggests, and we'll get into where the analysis actually lands. Here's where the paradox in the title resolves, and it resolves in a way that's less satisfying than most paradoxes, because it turns out there is no winner. The 1980s Sea Sparrow lineage doesn't outshoot the SM6 because it's a better missile. It isn't. The SM6 is a more capable weapon by almost every technical measure. Longer range, more sophisticated guidance, larger engagement envelope, greater flexibility. The reason the ESSM holds the last defensive ring is not because the Navy chose an inferior weapon by mistake or by budget constraint. It's because the physics of the close-in engagement, the radio horizon, the compressed timeline, the quad-pack density, define a problem space where the SM6's advantages become irrelevant and the ESSM's characteristics become decisive. Range is irrelevant when the target appears at 18 kilometers. Active guidance is equally available in both systems now. What matters at that point is engagement geometry, launch to intercept time, and how many rounds you can put in the air in the first 10 seconds. On those three variables, the ESSM quad pack is the correct answer. It costs less, it fills cells more densely, and it was designed, originally in the Cold War, and refined since, specifically for the close-in intercept problem that physics guarantees will exist regardless of how capable the outer layer weapons become. The deeper point, and this is where the strategic picture gets genuinely uncomfortable, is that the Sea-Skimmer threat is specifically designed to exploit the radio horizon. The adversary knows the geometry. The terminal phase of a Sea-Skimmer attack is engineered to arrive in the engagement window where the defender has the fewest seconds and the least decision time. The missile's altimeter holds it at 4 meters, not because that altitude is aerodynamically optimal. It isn't, and it introduces real challenges for the weapon's own stability in rough seas. But because 4 meters is where the curvature of the Earth shields it from the defender's radar until the last possible moment. Every design choice in the Sea-Skimmer's terminal profile is a response to a specific characteristic of the defender's sensor architecture. The ESSM exists because that window cannot be closed by buying better long-range missiles. It can only be addressed by having enough close-in rounds to handle the leakers that will inevitably survive the outer layers. The strategic weight of this plays out in the Western Pacific in ways that go beyond any single ship or any single engagement. The Arleigh Burke-class has served as the surface warfare backbone of the Pacific Fleet for over 30 years. The ships are capable, the crews are highly trained, and the Aegis system continues to be upgraded. The AN/SPY-6 radar on Flight 3 Burkes represents a significant improvement in detection sensitivity that pushes effective tracking range against low-altitude targets outward, buying some additional seconds of engagement time against the Sea-Skimmer problem. Those additional seconds matter. Every second of additional warning translates directly into additional engagement opportunity at the ESSM range band. But the fundamental constraints remain. Magazine depth is fixed by hull size. cell count has not grown. The mixed decision between long-range reach and close-in volume is a zero-sum trade that each ship's commanding officer and the strike group commander must make before departing port, without knowing exactly what threat profile they will face. What the broader geostrategic picture adds is the question of sustained engagement. A single engagement. One wave of sea-skimmers defeated by a well-loaded Arleigh Burke with a deep ESSM magazine is solvable. A sustained campaign in which adversary forces generate multiple salvo waves over hours or days, while US surface forces are operating far from a port where they could reload, creates a magazine depletion dynamic that individual weapon qualities cannot address. The best missile in the world, in a cell that was expended in the first engagement wave, is not available for the second. One detail that keeps coming up in open source analysis of Pacific Fleet exercises is the reload timeline at sea. Replenishment at sea of MiG-41 ammunition is not the same as refueling. Bulk liquids can be transferred underway at reasonable rates. Missiles in canisters require different handling, different ship configurations, and in a contested environment, the logistics ship performing the transfer becomes a target. The supply chain that feeds the ESSM and SM-6 magazines stretches back to production facilities in the continental United States and requires a functional logistics chain to be effective. Adversary planners who understand this, and Chinese naval doctrine explicitly addresses the logistics vulnerability of US forward-deployed forces, design their approach to stress that chain as well as the magazines directly. The Arleigh Burke and its MiG-41 system are not weaknesses in the US Navy's surface warfare architecture. They are the current best available answer to an extremely difficult problem. The ESSM quad pack is not a legacy compromise. It's a deliberate, well-reasoned solution to the physics of the close-in engagement that no amount of procurement of more expensive weapons can replace. But the solution is bounded by a fixed cell count, a finite magazine, and a logistics chain that assumes a permissive environment for resupply. Will the Flight 3 Arleigh Burke, with its improved SPY-6 radar, buy enough additional detection time to shift the balance back toward the outer layers and reduce the demand on the ESSM close-in magazine? Or does the adversary simply adapt by flying lower, flying faster, or increasing salvo size to absorb the improved detection range without changing the fundamental geometry of the problem? Nobody in the public domain has a clean answer to that. The engineers working on the next generation surface combatant, the program that will eventually succeed the Arleigh Burke, are working on that question right now. What they do know is that the MiG-41 cell count needs to grow, that magazine depth is the binding constraint, and that the ESSM quad pack is not the last word in close-in defense. It's the current answer to a problem that will keep evolving. So here's the question worth sitting with. If a ship commander has 96 MiG-41 cells and needs to choose between maximum SM-6 reach to engage threats as far out as possible, or maximum ESSM quad pack depth to handle the leakers that the outer layers miss, which choice actually keeps the ship alive in a multi-wave engagement against a peer adversary who has designed their attack specifically around the radio horizon problem? Each option has a cost measured in cells, and the cells you commit to one layer are unavailable for the other. Drop your reasoning in the comments. We read them. And if you want to understand how the Phalanx CIWS and the RAM system handle the targets that slip past even the ESSM layer in that last-ditch 5-kilometer window, that breakdown is next.